Hi everybody, welcome to physics. It's Mr. Duffy, and today's lesson is going to be about static equilibrium. To do that, we're going to start off by talking about net force, finding net force. Now, I talked about this in the first lesson in this unit. We talked about the law of inertia. So the law of inertia, we had to add up our forces, and again, if the net force was zero, it's just going to keep doing what it's doing. And so that's kind of where I'm going to kind of continue on here with us. Basically, the net force, the sum of all the forces acting on an object, is the net force total. And for static equilibrium, that net force is going to come out to be zero. So the sum of the forces is going to come out to be zero. But we're going to, again, talk about that and get to that point here in a second. So how do we find the net force? Well, in the previous problem, we didn't have any numbers to that free body diagram, but imagine scenarios where we do. When we have the individual forces that we can use, basically we just add them We resolve them into x and y components, and if they're at angles, and then add them up to see what their overall net force is. So here we have basically 4 newtons to the north. We would say that is positive 4 newtons because it's going up. We denote that as positive. And that would be a negative 4 newtons going down. So the overall net force would be 0 newtons. That's the basis for finding net force. Now, obviously, that's an easy problem. So is this one, but this one does not end up with a 0 net force. It ends up with, again, we have 6 newtons to the right. We normally say that's positive. We have 12 newtons to the left. We normally denote that as negative. And so our net force would be negative 6 newtons. Or we could say 6 newtons to the left. That would also be an acceptable answer. So again, that is finding net force. Now you can imagine the scenario where we have more than 2 forces. In this example, we have this free body diagram where there are 5 different forces acting upon it. But again, it kind of just, again, resolves itself down. These are all in the x and y directions. So we have a positive 5 and negative 5. Those cancel out to the horizontal. And then we have 2 down. That's negative 2. And then we have positive 1 and a positive 3. That adds up to 4 newtons total up. And so that we would end up with 2 newtons up as our overall net force. So again, we could just resolve it into the x and y's, and this one, again, just entirely x and y's. Now we might also have a story problem, in which case we're trying to find the net force of an object. So it says a gust of wind blows an apple from a tree. As the apple falls, so the gravitational force on the Newton or on the apple is 2.25 newtons. So 2.25 newtons here, and that would be the weight of the apple or the gravitational force. And then the force of the wind is 1.05 newtons to the right. Well, this is our first problem where we've come to, where we have, they don't, again, resolve each other into x and y. We have a y direction and an x direction, but not, not total, not the x's or the y's aren't canceling each other out. So what we're going to do is we're going to turn this into a right triangle, which again is totally fine. 1.05 newtons to the right and 2.25 down. We want to find that hypotenuse. We want to find the magnitude and direction, since forces are vectors, to find the the overall net force acting upon the apple. So let's find the magnitude first. A squared plus b squared equals c squared. We're looking for c. C is going to be the hypotenuse, so 1.05 squared plus 2.25 squared, and then the square root of that. Comes out to be 2.5 newtons. That is one of the answers, not the entire answer yet. We also need a direction, so let's find that angle there. I think the easiest way to find that angle would be tangent. So tangent -1, so inverse tangent of my opposite over adjacent. Opposite is 2.25 over adjacent 1.05. That'll get us our angle. So you could have used any trig function though. We get an angle of 65 degrees. So that would be 65 degrees south of east. There we go. We have a magnitude and a direction. So finding that force can still be, again, very similar to some of our motion problems. So again, nothing new in terms of trig functions here. Now, let's get back to where we were focusing on for today, is the fact that objects in equilibrium. So the law of inertia says an object wants to keep doing what it's doing unless it gets acted upon by a net force. Well, equilibrium means that there is no net force. Basically, again, the objects are either at rest or moving with a constant velocity, so the net force acting on the object is equal to zero. Basically, what that kind of sets up to our problem, if we know that, again, the net force is the sum of the forces, like again, like force 1 plus force 2 plus force 3, however many forces there are. But if we know that this always comes out to be zero, the sum of the force, if we know it's in equilibrium, then we know all these forces are going to add up to zero. So again, maybe I have force 1, and I have force 2 is, let's say, 20. I know that force number 3 has to be negative 30, that's basically how it works out. So again, I would be able to figure out, since I know that it adds up to zero, I know that my final force is the remainder. Okay, so let's put that to practice. Here's a problem where we've got, again, x and y values, and we're, again, looking at equilibrium. So I have 6 up, 6 down, so those, again, are going to cancel each other out, positive and negative, and we have 8 newtons to the right and 8 newtons to the left. So the overall net force is 0 newtons. I guess I could have written it a little bit differently. I didn't, but I could have. So maybe, let's see, I'll just erase some of the stuff. We can imagine a different scenario of the same problem. Let's just say I've got, meant to fill it. Okay, so let's just say I just made this up, but we already know the answer, obviously. But okay, so it's that maybe we know that the net force is 0 newtons entirely. So the question might be, what is the force to the right? So again, we have 6 newtons up, 6 newtons down. We have 8 newtons to the left. Again, by doing that, we know that we would be 8 newtons to the right. That would be, again, another good example of a net force type of problem. Static equilibrium. Again, another word is static equilibrium. There is another type of equilibrium we'll talk about in a later chapter. So again, this is static equilibrium, balanced forces. Okay. Now, here is the part you really want to pay attention to. So this is what your homework is going to be like. This is a static equilibrium problem. This is a level 2 problem. Your homework is a level 3 problem, so just a slight bit harder than this, but you're going to be able to handle it once I go through this example. Static equilibrium is basically, again, saying that the forces are going to add up to be zero. So this is going to be, again, the net force is going to be zero. And what we're going to be trying to do is finding the tension force in the green and the red strings. Okay, now in this level 2 problem, both the ropes make an angle of 31 degrees. So that's kind of like something that's given to us. In your level 3 problem, those angles are going to be different, but that's really the only thing that's going to be different in the problem, is that those angles will be different for you in a level 3 problem. So what we have to do is, again, we know that the forces are balanced out. That means our vertical, our y components are going to equal our x, are going to be equal to 0, and our x components are also going to be equal to 0. So we have to figure out what our, what our y, what's going on, what's pulling down. So we have this weight attached to these two different strings, and actually a mass, and we need to turn it into a weight. We know that gravity pulls down at 9.81, and so this is kind of the new part, I guess, of this lesson. We'll come back to that a little bit in a later lesson, but basically we need to multiply our mass in kilograms times 9.81 to turn it into a force. And so this equals 25.5 newtons. And that would be down. It's being pulled down because gravity pulls directly down. Which means, and this is the way I'm going to draw my triangle here, since it's in static equilibrium, I know that I have 25.5 newtons back up. Okay, again, those have to equal each other. The down has to equal the up. Okay, now there are 2 ropes though. So the one rope is pulling off to the right and the one rope is pulling off to the left. Again, I know that these amounts have to equal out to each other. Okay, they're gonna equal out. That again because it's in static equilibrium. So, and also again, I know they're going to equal out too because these are exact same triangles. So the only thing that I'm left to solve for is again, um, well, actually, I don't even need to solve for the x side. I just need to solve for the hypotenuse of the triangle, and those are going to be the exact same. So I still need to solve for what is this angle on the inside here. I know that that's a right triangle there, so it's going to add up to 90 degrees. So if the outside portion is 31, then the inside portion is going to be 59 degrees. Okay, so I guess I was going to do some tangent to find the x value, but I don't really need to solve that. I can use sine because I have the opposite side and I want to find the hypotenuse, so I could just definitely do that. So sine of 59 is equal to my opposite, 25.5, over the force tension in the green string. But the force tension in the green string is going to be equal to the force tension in the red string, so I don't really have to worry about that either. And let's see what it comes out to be. Sine of 59, 25.5 divided by that answer is 29.7 newtons. Now, that is the answer, and that's the answer for the other force tension as well because they are identical triangles. And so, sorry about that earlier. I mean, I was going to solve for the x value. It would have just given us a little bit more information, but it wouldn't have been necessary. We could have used Pythagorean theorem after we did that, but again, just using sine I think works just as easily. So it allows us to solve the same way. Okay, so when you get to a level 3 problem, again, you're going to be doing it exactly the same way. Make sure you multiply the mass times gravity, 9.81, to get yourself a force down. And then that force down is going to be equal to your force up. And then you're just going to have different tensions in the different strings because they're going to be at different angles. But still, going to be able to do the problem. And hopefully this video helps you understand a little bit more what static equilibrium is all about and how to solve